Okay, the time has come for us to start charting a course into the murky waters of networking inside of Kubernetes. And I promise we're getting there. But showing rather than telling is always my style. What I'm going to do here is I'm going to create a deployment. It's going to be using Nginx. I'm specifying that the port is port 80, and I do need to put the 2 dashes in front of that there, because that's something that's going to be important for later. I also want there to be 3 pods made by this deployment, and there you go, a nice quick and dirty deployment. Now, what I'm going to do next is that I'm going to create a service exposing this deployment. Now, what is a service? Thing is that in Kubernetes, for any pod to be communicated with, what it basically needs is a great big neon sign like you'd see flashing inside of Las Vegas, basically saying, here it is, here's the pod that you're looking for. Why is that necessary? Well, let me show you something interesting. If I do a kube control get pods, and let's get a few extra columns of information out there, you can see that each and every one of these pods has its own unique IP address, right? Now, if I were to delete one of those pods, let's just go ahead and delete the very first one that you see there. Now, that's 247.34. It's on node 2. What guarantee do you suppose there is that that pod, when it gets rebuilt, and it will have that exact same IP address, or even that'll be on that same node again? Like, practically none. All right? And that's an entirely different IP address. It's still on node 2 because the scheduler figured, oh, there's nothing on node 2. But point is that IP addresses, they change. And as deployments like get scaled up and down, and as pods get deleted and so on and so forth, IP addresses are a constantly moving target. All right, so this is kind of the nightmare we find ourselves in with Kubernetes. Fortunately, we got a really cool, really clever solution here. Now, I'm going to do this using a kube control command, although we certainly could write a manifest to do this. I'm going to expose the deployment called demo deploy. And as a result of that command, what just got created was a new type of object called a service. There are 3 different kinds of services, which we're going to talk about a little bit later, but the one that we just made and is most common is known as a ClusterIP service. And notice that this service has its own IP address. All right, now why is that relevant? I'll show you in just a second. Now, let's get all those pods up and visible one more time again. Get pods output wide. And let's open up another pane here. Do a watch kube control describe our service called demo deploy. Now, what you're seeing inside of this description is, well, a couple of things. But for one, I can see the IP address 172.16.3.105. That's one. But there are 1, 2, 3 other IP addresses here. Where do you suppose those are coming from? You might have already guessed, but those are the IP addresses of all these pods that you see over here. Right? Each and every one of them is being matched up. And what's super cool about services is watch what happens when I scale the deployment demo deploy from 3 replicas down to just 1. 2 of those pods get deleted, and look what happens to the service automatically. It just tracks the IP address of the 1 remaining pod. And if I scale that up to like 10, the next thing you know, bip, 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 1, 2, 3 plus 7 more, 10 IP addresses. So as chaotic as pods getting created and destroyed are, here's what's really nice. Between all those changing IP addresses, do you see the IP address that did not change not even once that whole time? It's the IP address of the service. So think of it this way. If the service always knows where the IP address of the pod is, and pod IP addresses change all the time, if you know the IP address of the service, you're gold, because the service is what will point you in the right direction. So that's the method behind the madness, and that's how services work. We're going to talk more about those in greater detail, but first, we need to set some ground rules. All right, so what do I mean by that? Well, now that that deployment has been exposed by a service, it means that other pods inside of your cluster can actually talk to those pods. So to do that, I'm going to make this pod here. It's going to do all my talking for me. This pod called client is running BusyBox. And BusyBox is nice because it lets you execute commands like curl, and we can see if we can use it to get network connectivity. So I'm going to go ahead and I'm going to make that pod client. I'm going to kube control exec inside of that pod. And I do have the curl command inside of this. Never mind, I'm not going to use curl. I'm going to use wget. And what I'm going to do is that I am going to do this. Inside of my container, I'm going to type wget, then the name of the service, demo deploy. Now, remember, the service is what is pointing to the pods. The pods in my deployment are all running Nginx images. So when I say I want to download like whatever is at that service of that pod, look what wound up happening. It downloaded index.html. What's that? It's the welcome to Nginx page. How cool! We've just had pod-to-pod communication. We downloaded the welcome page. And right now, every pod inside of our cluster is able to do that. They can access and talk to and work with the pods inside of that deployment. It's peace and love, man. Everybody loves everybody, man. That's the security nightmare. So we need to control this. While yes, pods do need to communicate, we also need to set rules about which pods are allowed to talk to which pods. And to do that, we're going to create a new type of object called a network policy. And I'm not going to lie, network policies from all of the hundreds of students that I've worked with in Kubernetes is just the most nightmare of a manifest you'll ever see. Look at this thing. Ah! Granted, not all network policies are this big and ugly, but if I can teach you how this network policy works, then there's no network policy out there that's going to faze you. All right, ready? Let's get down to it. So network policies, much like resource quotas and limit ranges and other things, are assigned to namespaces. So you attach the network policy, and what that means is that this network policy is going to affect just those pods that are inside of this specific namespace. So that's an important thing to point out right off the bat. You need to target the namespace of the pods you wish to control, right? So that's step number one. Step number two, when we crack open the spec, whoo, boy, all right. Basically, network policy, if you boil it all down, is really simple. It's all about controlling ingress and egress, which is to say traffic that is coming in and egress, which is traffic that is going out. You can configure network policies to control both, or just one or the other. I always kind of visualize a network policy as like a helicopter parent. You know, somebody who's like right on top of their kid, like all the time. Like, I don't want you talking to that Jimmy down the street. No, he's not good people. Rah. All right. Like, I want you to only talk to that boy Melvin next door. Oh, he's a good kid. Rah, rah, rah. That's exactly how a network policy works. All right. So, policy types is where you list what things is this network policy going to control. Ingress, egress, both, just the one, you get it. Pod selector is where we basically are saying what pods are we controlling using this network policy. So if the network policy is the helicopter parent, then who's the kid who's getting parented? And what we're doing here is we're using match labels, just like we did with deployments. Like I said, labels are so important in Kubernetes. And basically, the way this works is that if you are in the default namespace, and if you have the label role DB, you are about to have your traffic coming in and coming out controlled, and certain criteria has to be met. All right? So let's go on down to the bottom part. Here and here is where we're going to be setting up what are the rules that have to be followed in order for traffic to actually work. So for ingress, here we're making our first list of rules. We're saying that traffic has to come from one of the following sources. Now, you don't have to use all of these. In fact, most folks won't. But again, this is the longest and dirtiest example that I could find, so we'll just go ahead and use that. IP block allows us to specify a CIDR range of IP addresses. Like, it's got to be that pod in this range, otherwise we're not going to allow that pod to send ingress. Except, and you can advertise exceptions, if it's in like this range or this particular one right here, that it's going to be not allowed. Pods can talk to each other across namespaces, which is interesting. So even if pods are in different namespaces, if one is exposed by a service, it's not safe. Other pods and other namespaces can access it. So namespace selector is where we can say that, hey, pods in the default namespace that have the label role DB, you are only allowed to receive traffic from pods that are in this IP address range, or pods that are from any namespace that has the label project my project. So again, this is going a label that's on the namespace itself. You can put labels on all kinds of different things. So in other words, must be from this namespace or must be from this IP range. Or, and this is the most common way, honestly, that we see these getting established, pod selector from specific pods. Like, it must be from pod with this label role front end. So to go back through all that one more time, listen up. All pods in the default namespace that have the label role DB, the following changes are about to go into effect. You may only receive incoming traffic from pods in this IP range, or pods from that namespace, or pods that have this particular role. Make sure that you're being very careful with the rules of how network policy works, because these are all or situations, and you gotta make sure you're really spelling out very particularly in a test environment that that's exactly what you mean and what you need. What you can also do for ingress is that for ports, you can specify, all right, pods that are being targeted by my helicopter parenting, you can only receive traffic into port 6379. You could also list other ports if you want. Unfortunately, egress is very much the exact same thing. It uses very much the same language, except now we're saying, all right, pods in default with the label role DB, you are only allowed to send traffic to pods inside of that IP address range. And when you do send it, you're only allowed to send it to their port 5978. So you can mix and match all of these in either section, or you can choose to not include them at all, which is perfectly fine. All right. But make sure that you're being very precise with the rules you're putting in your network policy, and test, test, test. So very quickly before we move on, let's demonstrate actual network policies in practice. Now, there are no network policies in my system at all at the moment. I can, inside of my client pod, send a request to another pod, an Nginx pod, and right there you can see I downloaded that index.html file. But what I'm now going to do is that I'm going to apply this network policy that you see here. And what you're seeing, this is what's called a default deny network policy. What's happening here is that all pods in the default namespace are about to be told where they are allowed to receive traffic from and where they are allowed to receive traffic to. Pod selector open close curly braces means all pods. So we're selecting all the pods in the default namespace. Now, looking at that network policy, where are the rules that say what we are allowed to do? Because remember, a network policy, if you aren't doing what the policy says is permitted, it's not permitted at all. Oh, shoot. We never actually gave any rules to like what exceptions there were, which means that this is why this is a default deny. Watch when I run this wget command again. It's hanging. It's not going to connect. So the network policy is kind of slapping our hands here, so to speak, and that's no good. We need to change that up a little bit. Now, if we go back and we take a look at the manifest for my pod that is trying to access Nginx, it's got the label run client on top of it. Basically, if this is what I want to do, if I want my Nginx pods to be able to accept traffic from pods that have the label app Nginx, then here's what I would need to do. I would first need to see what are the labels that are on my deployment pods. Looks like they've all got app demo deploy as their label. So let's go over here, and for pod selector, we're going to change things up a little bit. Match labels, app demo deploy. So now this network policy is no longer applying to all of the pods inside of the default namespace, just those deployment pods. And I'm not too worried about egress. I'm worried about ingress, traffic going into those Nginx pods. And what I'm now going to do down here below is, and I'm just going to paste this in, is that we are going to specify where is ingress allowed to come from. Ingress to my Nginx deployment pods can only come from pods that have the label run client on them. So having made those changes and running kube control apply to my network policy, so the policy has been updated. My client pod using BusyBox is still up here and running. I'm going to run wget one more time and see if it works. So what we've successfully done is that we've been able to configure our network policy to allow this specific interaction, although literally any other interaction that these deployment pods are trying to make would be prohibited. All right, we got a little death by PowerPoint coming your way here, but hopefully it's going to clear up a few things. Now, we had made a service prior by using the kube control expose command. This is what a service manifest looks like. It's not super terribly difficult, but again, notice that we're using selector just like we did with deployments, just like we were doing with network policies, to say which pods are being affected. So our selector is choosing this pod, our selector is choosing this pod right here. It's got that label. Now, the question is what are the meanings of these port numbers that you see right here? Well, the thing is that target port refers to the port that is on the target. And since we are using Nginx inside of this pod, remember, Nginx's container port is 80. That's written in stone. That's not something that you can change. Port, this value right here, is actually the port on the service itself. And what this is doing is that it is mapping a direct relationship to say that, hey, if you go to this service at this IP address, and you go to that port at that IP address, 3423, it'll take you to this port, to that Nginx container, allowing you to access the application. Now, the reason why that exists is let's expand this a little bit. Boop. It is possible for pods to have more than one container inside of them. And if a service is going to redirect traffic to that pod, well, how am I supposed to be able to access the specific container that I want? Well, the same rule here still applies. If you go to this service and you access it through that port, it is going to take you to port 80, which is going to connect you to the Nginx container. But look what we can also do is that we can add a whole other port protocol here that if you go to, say, port 4444, that'll take you to port 8888, which is running some other application. So services can be configured to go to different ports, even if they are entirely different containers, inside of the same pods that they are exposing. So that's the difference between port, target port, and just wait, because it's ports aplenty over here. We're going to be talking about node ports. All right, in this animation, we are going to start talking about pod-to-pod communication and services in a visual way so that you can see how these tools work and interact, which hopefully is going to help you understand that Kubernetes does a lot of networking stuff under the hood. It's really nice to not have to worry about these things on a day-to-day basis, but you really do need to understand this stuff, in my opinion. So in the story that I'm telling you, super simple cluster, one node. There are two pods, they're on the same node as each other. And pod number 1 there is all like, oh, gee whiz, I'd really like to talk to pod number 3. So how does that work? We know from what we've learned earlier that pod number 3 needs to be exposed by a service. Now, let's say that that service is already created. But the question is how is that service located? How is it accessed? So on and so forth. Here is where the great and mighty kube proxy is going to come into play. And kube proxy is a lot like kubelet. Kubernetes loves putting the word cube inside of everything. And there is a kube proxy located on every node inside of your cluster. And what kube proxy has access to is the IP table of every single node inside of your cluster. Which means that the kube proxy is perfectly able to look and see, there's a service here called pod 3. The IP address that service is exposing is 10.1.2.1. That's the IP address of the pod. So in this case, the kube proxy's job is very easy. It checks the service. It sees that that service is pointing to just one pod here. And as a result, whoop, our pod is given the IP address, and then routing is able to take place. Once the IP address of the pod is located, it's game over, all right? That's the end goal here. But remember that the headache that we face with Kubernetes is that we have dozens, if not hundreds, of pods with constantly changing IP addresses, so we need some method on top of this madness. Now, let's scale it out a little bit and let's get a slightly more difficult scenario. Let's say, once again, we've got a pod that really wants to talk to one of those pods inside of the zombie deployment. We just named it zombie. Because all of these pods are identical, they're all replicas, right? It doesn't matter which pod this pod talks to, okay? So that's an interesting conundrum, because once again, we reach out to great and mighty kube proxy for connection advice. So what kube proxy is going to do is that it's going to check its service table. It's going to find one called zombie, and it's going to see that there are 3 IP addresses to choose from. The kube proxy is responsible for setting up the rules on, or rather obeying the rules of which IP address gets selected. And what will wind up happening is that it will use a round robin by default approach that, hey, if the last time somebody came knocking on my door asking for a zombie pod and I sent them to 1.3.1, this time I'm going to send them to 1.3.2. So it's kubeproxy that's ultimately making the decision here which one of these 3 pods is going to be the one that winds up talking to BusyBox. And what also happens as like a part of that process is that kubeproxy will also make sure that that pod is healthy before a decision gets made. So if this pod is still in container creating or it's erroring out, then that pod won't get chosen. It'll instead hop down to the next one, and then it will choose that pod instead. So in this story, we'll say, hey, I'm going to go with node 2. All right, that's just how the cookie crumbles in this story. And now we're going to take it even further back. Once again, let's say that we've got a deployment that's making pods. A deployment's making 3 identical pods. 2 of those pods happen to be on node 2, and 1 of those pods happens to be on node 3. That's just the way that it works out. And now that we're looking at a multi-node cluster, everything that I was telling you about kubeproxy applies to all of the nodes. Now, take a look at the table that I've got in each one of those nodes that you see here. What do you notice about it? They're all the same, right? So it doesn't matter where you go. Any kubeproxy in any node, whether you have a cluster of 1 node or 50 nodes, they're all going to have access to the same routing information. So this begs the question, how is one going to connect to one of those pods? Well, before I move on to the next point, let's do a little exercise here real quick. Suppose that I have a pod down here in node 3. This is using a BusyBox image. And let's say that it needs to talk to one of the zombie pods. And it says, oh, great and mighty kubeproxy, please pick a pod for me. kubeproxy goes and it looks at all these IP addresses. Is it a guarantee that kubeproxy is going to choose 10.1.2.1? No, not at all. That is not important. It can't be important. kubeproxy will use round robin to determine what the next pod is going to be chosen. So my pod that I drew right here might wind up talking to a pod over on top of this other node. And that's okay. Because think of it, if that pod had been created over here on top of node number 1, and I said, hey, I needed to talk to one of those zombie pods, I'm going to have to wind up talking to a pod on a different node anyway. So because things are always so chaotic, we can't be taking the time to think, oh, is this pod on the same node as this other pod? That doesn't matter. All right, now, everything that we've just been describing, pod-to-pod communication, has all been a specific type of service known as a ClusterIP service. And there are 3 types of services. There's the ClusterIP service, there's a NodePort service, and there is a LoadBalancer service. And each of these services build on the one that came before them. So if we have an idea of how ClusterIP services work, let's take a step up now to a NodePort service. Now, what you'll see here is that our tables have changed somewhat. Our zombie services are no longer ClusterIP services, they are NodePort services, which means they have a node port. This will always be a number between 30,000 and 32,000 something, 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 right? Point is, node ports are always very recognizable. All right. Node port services are the most primitive type of service that actually allows external access into the cluster without using kube control. Check this out. If you have a client who has the IP addresses of one of your nodes and has the node port of one of your services, that client is able to access whatever pod is being pointed to. So let's walk that through. If I were to send a curl to 192.168.0.12, that is this node right here. When we reach that node, we are accessing it via port 31234, which is the node port that's attached to our zombie service. At which point, guess what? The kube proxy says, I see you're trying to access zombie. And then the exact same behavior from before occurs. Kube proxy is going to use round robin to determine which one of these pods should we go to next. Is it guaranteed going to be this pod? No, we've already said that. It's going to use round robin to choose. So if it turns out 10.1.3.2 is the IP address that gets chosen, even though we sent a curl request to node 3, we wind up accessing a pod on node 2, which is perfectly normal. And if that seems strange to you, well, imagine if we had a 50 node cluster and there's one pod on those 50. You have a 1 in 50 chance of guessing the correct node. That couldn't possibly work. So that's how node balancers work. That's how NodePorts work in a nutshell. And it's a method of how you can access your pods ultimately from an external connection. Now, the third type of service that we're going to talk about are load balancers. And load balancers are more sophisticated. Load balancers still use NodePorts, as you can see here. But a load balancer requires some sort of external machine to your cluster with an outward-facing IP address to accept incoming traffic. If your Kubernetes cluster is in the cloud, those folks, Azure and Amazon, they love to take your money and they'll spin up a load balancer for you. It's coming from a place of jealousy because, like, we all do all our work on bare metal. But point is that you do need to provision that. Kubernetes does not come with load balancers. It's happy to work with load balancers that you will provide it, but that's not something that is included. But once you have a load balancer, what's nice about this is that your client can now go to that load balancer instead of going straight to one of your nodes inside of the cluster. And what the load balancer will do is that it'll say, all right, enough of this round robin stuff, which is not true load balancing. I'm going to make a educated decision about which pod is going to wind up getting selected. And thanks to the fact that load balancers also use NodePorts, it can choose whichever node it wants. It can access the IP table through the NodePort. It can choose the IP address of the pod that it wants and can ultimately chart routing that way. All right, it's picture's worth 1,000 words. Let's get down to the command line and let's actually make some services and let's see how NodePorts work. So I've created this pod here, and before I start setting up any services at all, I'm going to go ahead and open up a port forward, and let's just do port 2224, and that is going to port 80. And so long as that port forward is open, I can curl localhost. And the way that this is set up is that inside of this pod, there is a endpoint which is called /static. And that's just a little repository that has a file in it called nginx.txt. Inside of that little txt file says, you done did a networking. Ha ha ha. So notice I needed a port forward in order for this to work. Like, I needed kube control access in order to access what was going on inside of that container. All right, but we're going to change that, because what we're going to do next is that we are going to create a, we are going to expose, that pod with a NodePort type service. So we're going to do kube control expose pod nginx configured. And what I need to explicitly state here is that our type is NodePort. By default, it's going to be ClusterIP otherwise. So I'm going to go ahead and expose that pod. That created the service. And if I were to describe the service that I just created for nginx configured, it's pretty much the same as what we'd seen before, but notice that the type says NodePort, and that there is also now a field NodePort 30337. That was assigned automatically. So that number right there, 30337, is something that we need to remember. Now, what I'm going to do is this. Let's get that curl command back in here. What I'm going to do is that I'm not going to through my local host's kube control connection. I'm instead going to go to one of my nodes. So let's do it this way. Kube control get nodes output wide. The IP address of my first node is 10.14.24.245. Let's do this. I'm going to curl, that's node number 1. I'm going to go to that node port 30337. That should access my service, which should access the pod. Which means that if I throw /static/nginx.txt onto the end of it, you done did a networking. Super cool. This is just a straight curl command. I'm not using kube control or any other kind of special permissions. I just had the IP address of the node and the node port. Now remember what I was telling you earlier, that it does not matter what node the pod is on. As long as you are using the IP address of one of those nodes, it'll work because kubeproxy is everywhere. So to prove it, I'm going to grab the IP address of my second node right here. And let's run this again. This is the IP address for my second node. Same node port, same everything else. Still works, which just, again, is just kind of the proof that node ports are accessible and can be used to track pods no matter where you are in the cluster. And if you are planning on taking the CKAD or the CKA exam, it's pretty much a guarantee that there will be some node port service related question on that exam. And there you have it. That's our crash course in Kubernetes fundamentals, but there is still so much more to learn. Though we've covered everything in this course from YAML all the way up to networking, there are still many more things that need to be learned in order for you to especially pass the CKA or the CKAD exam. That's why I recommend that if you truly wish to master Kubernetes, get your hands dirty, and do what you need to do to succeed, check out Alta 3 Academy. All this content and way more is waiting for you, including a work environment, the same environment that I was using in this demo. An AI instructor that will answer any question, no matter how simple or complicated. Plus, full mock exams for the CKA and the CKAD so you can test your skills and make sure that you are really learning and prepared to get out there and take Kubernetes by the horns. So click that link down in the description and take the next step towards becoming a true Kubernetes expert. I hope to see you there. Make sure that you like and subscribe, and I'll see you next time.